In today's video, we will see how we can create a quantum circuit. We will make use of IBM's quantum computing facilities for this. As I said, we will be using IBM's circuit composer for creating our first quantum circuit. To do that, you need to create an account in the IBM Quantum Experience website. So you should go to this website shown here, quantum-computing.ibm.com, and then create an account for yourself. It is free to create an account. Once you create an account, log in using your credentials. And once you are in the home page, you have three different options under tools: results, circuit composer, and Qiskit notebooks. So we are interested in circuit composer. So you go to the circuit composer, click that, and it brings you to the your circuit composer page. Right? There's a blue button here which helps you create a new circuit. So you click that, you click, and then you comes to the composer page. In this composer page, the first thing you need to do is to name your circuit. So let us say my first circuit, right? And then you save it. Go to file and save that. So now an empty circuit is created. Okay, now we need to decide. When we look at it, we'll see for me it comes with 5 different lines here, right? So what these 5 lines are, we'll see in a minute. And then there are a lot of gates here which you can drag and drop here, and then there are some operations here. There's a barrier operation here, etc. So what these things are, we'll see one by one. Okay, first things first, you can click the settings button. You click there. There's a description space for you to write something about your circuit. This is my first quantum circuit, and that's done. Then it asks for quantum registers. How many quantum registers you want? So what a quantum register is basically just like a normal register. It consists of bits. How many bits should your quantum register should have? I can have one quantum register with 1 bit. I can have one quantum register with 5 bits. I can have 2 quantum registers with 5 bits, etc. So if I want to add one more, I can click here. So there are 2 quantum registers that I created. One is Q, one is named as Q, one is named as R. I can create another one which is U, etc. Right? I can delete those registers completely, and I can have only single register, and I can have just single register with just 1 bit, right? So that is quantum bit. So this is 1 qubit, and this quantum register Q has just 1 qubit, so Q of 0. So if I have 2 qubits, we'll be having Q0 and Q1. And if I have another quantum register R, I will have Q0, Q1, 2-bit 1 register, another 2-bit registers R0 and R1. Then what is the C2 and D2? We will come to that in a minute, right? So C2 and D2 are classical registers. So if you can see that it says synchronize classical registers with quantum registers. So it says that the number of classical registers will be in sync with quantum registers. So if you have say 2 quantum registers, Q with 3 qubits and R with 2 qubits, you will have 2 classical registers with C with 3 bits and D with 2 bits, right? You can override it by unchecking this button over here, and then you can decide how many classical registers you want as well. But why is it usually synchronized with quantum registers? Because for each quantum register, when we measure that quantum register, what happens is whatever value in that quantum register is pulled out and stored in a classical register. So it is good to have same number of classical registers as quantum registers to do this, right? So now for the time being, let us just have 1 quantum register, and let us have just 1 qubit in that, right? So this qubit is initialized to value 0. So everything is 0 initially. So Q0 is initially 0. And then before putting any operation, let us just measure that. So if I measure this, I should get 0 in one of the classical registers. So how will we see if I get 0 or not? First I will save the circuit. I save the circuit, and then I will run. The run button is in the right top corner. Press that. It will ask which backend you want to run your job. So there are different backends like IBM 16 Melbourne, IBM QX2, IBMQ Vigo, etc. We are going to run it in a quantum simulator. So quantum assembly simulator is what we are going to run it. So it gives the most accurate result because it is not a real quantum computer, it's a quantum simulator. So that is the ideal quantum computer that we want to work with. Right? The real quantum computers are not yet perfect. There are imperfections in real quantum computers even now. So there may be slight errors in the real quantum computers, but it's not that bad. It is getting better and better every day. So we'll run it in quantum simulator, and then it asks how many times you want to run this experiment. So if you remember, we discussed about this in the last video. Quantum computing is probabilistic. A qubit, for instance, we can put it in a state where it is 1 by root 2 probability, or half a probability that it becomes 0, half a probability that it becomes 1. This means that the qubit is in both state, but the probability that whenever we measure we see 0 is half. So to see probabilistic result, you need to run it a lot of times, right? So that is why it asks how many shots you want. So let us run with whatever recommendation they give, 1024, and we run the circuit. So when we run the circuit, what happens is the circuit is put in a queue. So pending result, we are waiting for the result from IBMQ QASM simulator. So now the result is here. We click that and another window pop up with the result. The result we can see in different format, but right now we'll be seeing it in a histogram. So you can see that 100% of the time the state of that qubit is 0. C1 is 0. So it will put the result in the show the result in the classical register. So classical register is also initialized to 0, but C1 is changed with whatever value that comes, that is 0. So it will be 0. So that is our first circuit. We have done our first circuit. Now let us go back and add some gates to it. So we'll see 2 or probably 3 gates today. Gate number 1 is an X gate. What is an X gate? An X gate is equivalent to a NOT gate, right? So what it does is, if the input to the gate is 0, it flips it to 1. If the input to the gate is 1, it flips it to 0, right? So if it is 0, it flips to 1. If it is 1, it flips to 0. So right now it is 0, right? So we should get 100% 1 now. Let us see if we run the circuit what we get. Run. It is pending result. Once the circuit is run in the QASM simulator, the new result will come in this tab. It will be result 2. Yes. So you click that and you can see the result as 1. The state is 1, 100% 1. Right? Let's go back to the circuit. Now let us make it a bit more fun. Let us add one more gate, or maybe even the single gate. I can remove this gate. Let me add a new gate called Hadamard Gate. Hadamard Gate does something really funny. What Hadamard Gate does is, it takes 0, and when you put Hadamard Gate to the when you give 0 to Hadamard Gate, what happened to that bit is that bit converts itself into a superposition state of both 0 and 1. To see that, you can actually go here and there is a tab here which looks like a histogram. You click that, it will show the visualization. So visualization, now it is state vector. The state vector now is both 0 and 1. This point, at this point, it is both 0 and 1. And what is the amplitude of 0 and 1 of this bit? The amplitude of this bit is 0.707. 0.707. 0.707 is 1 by root 2. Remember, the amplitude is 1 by root 2. The probability in which that bit appears is the amplitude square. So 1 by root 2 square is 1 by 2. So it is 1 by 2 0 and 1 by root 2 probability 0 and 1 by 2 probability 1. This j represent the complex number. So as I said, the amplitude in the last video, I told you this, the amplitude is a complex number. So right now this only has a real component, but it can also have a complex component. So now if you measure this, what will the result be? So before measuring, let us save the circuit, run. So when we measure this, what we are going to see, so while it get you create the result, let us go to the third tab here. This tab here shows a circuit editor. So this is the OpenCASM format. So basically it means quantum assembly format. So whatever you are dragging and dropping here, this is the real code that is running behind, right? So if you want to learn quantum assembly, you can learn it from here, but there is no point learning this. There is a much more better option that you can use Python program to create the same thing. That is what you have here as open Qiskit notebooks. So you can use that to create Python to run IBM's quantum circuits. Okay, the third result is here. When you click that, let us see what happens. So we have around 49.0% time we get 0, 50%, 50.97 times it is 1. So that shows that the state is 1 by root 2 0 plus 1 by root 2 1. So that is the state of this circuit, right? Now let us see one more circuit, and then okay, then let's do something fun. Let us add an X gate here. Okay, so when I add an X gate, you see the state vector, so all of a sudden it changed color. Okay, so let me delete that, so we'll see the difference. This was previously the state 0.707 plus 0j, 0.707 plus 0j. So this is a state of 0, this is a state of 1 for this qubit. If this is not there, this will be completely in a state of 1 and 0. So it is 100% 1 and 0%, 100% 0 and 0% 1. So when we add H gate here, it becomes, the amplitude becomes 0.707. 0.70 square is around 0.5. So you'll get 0.5 here probability. Now when I add X, what happens here? The 0 is converted to 1 and then an H gate is applied. So when this happens, it does convert 1 into a superposition state of both 0 and 1. So if you look here, the 0.707 and 0.707, the absolute value is the same. The sign changed to minus. So if it's a wave, it is in an opposite phase. So 1 is in the negative phase here. That is what it means. But the probability remains same, because when you take the square of 707, you get 0.5. If you take the square of minus 0.707, also you get 0.5. Right? So when you run this, you get very similar result as previously. Save. Run this. You'll get very similar result as previous, which is 50% 1 and 50% 0. We'll finish with one more circuit. What happens when okay, let us see the result first. When we go here for the result, you can see 0 is 48.82, 1 is 51.17, more or less the same. Now there is one thing that you may come across quite often. It says original circuit and transpiled circuit. So what is it? Does look this? It looks exactly the same, but what does this transpiled means? Transpiled is equivalent to compiled in quantum computing. So transforming one circuit, one form into another form is called transpilation. So what happens sometimes is we make complex quantum circuits where some gates can be completely removed, can be optimized. So that is what transpiled circuit basically means. Now let us see one or two more circuits and end this video. So quantum circuits are reversible, right? So the reverse of H gate is H gate. So if I put another H gate here, there is 0 coming with X, then an H, and then another H. What happens is it becomes 1, right? Let me remove this first. So it was 0 initially, so the state vector was 0, and then when I put X, 0 became 1. Then I put another X, what happens? It will go back to becoming 0. Same goes here with H. Let me put X, so 1X, so 0 becomes 1. I put an H, it becomes in a state of 0 and 1. Then I put H, it becomes 1, right? So now let me ask you a question. Let me change this so that you don't see what's happening. Let me put an X here. What happens now? What will we see? So think about what happens here and think what the result will look like. Okay, is it 0 or is it 1 or is it a combination of 0 and 1? I don't know. Try it yourself, try the circuit and see what the answer comes up. Post in comments the answer that you found or the answer that you think this will generate. See you soon in another video of quantum computing for dummies. Thank you.